let's try to solve this problem here. So the capacitance of a variable capacitor can be varied from 10 picofarad to 100 picofarad. So this is a capacitor that we can change its capacitance, and the minimum capacitance it can be is 10 picofarad, and the maximum capacitance that it can be is 100 picofarad. Okay, so it has a range, something like a rheostat, but rheostat you can change the resistance. This one you can change the capacitance. Okay, the capacitance is initially fixed at 100 picofarad and it is connected to a 25 volt battery. So let's draw the situation. Okay, most probably we have a 25 volt battery connected to you need a resistor definitely. Okay, you cannot just connect it directly to a capacitor. So the capacitance is initially 100 picofarad. Okay, let's sketch the situation. So C initial, it's 100 picofarad connected to 25 volt battery. Okay, so this is the initial situation. Okay, with the variable capacitor still connected to the battery. So if we still connect to the battery, one thing we know for sure is that the potential difference of the capacitor will still be equal to the potential difference of the battery when it's fully charged. Okay, again, the voltage of the battery will be equal to the voltage of the capacitor. This is what we know if we connect it to a battery. Okay, of course, after you fully charge it. Okay, you charge slowly, the voltage will increase. By the time you fully charge the capacitor, the voltage of the capacitor will be equal to the voltage of the power supply. If it's this kind of charging circuit. Okay, so what we know is if we do not disconnect the battery, if we still remain connected to the battery, what will happen is the voltage across the capacitor will still be equal to the voltage of the power supply. So the voltage will not increase, voltage will not decrease, the voltage will remains at 25 volt. Okay, so this is what we know. Final, your voltage, because if you are still connected to the battery, so I'll still draw the battery here. Okay, I know that the voltage initial is 25 volt because you're connected to this battery over here. Okay, let's write it more clearly. This is the voltage across the capacitor initial. Okay, voltage across the capacitor initial is 25. The voltage across the capacitor final will still be equals to 25 because voltage capacitor initial is equals to voltage capacitor final because you are connected to the same battery from initial to final. Okay, then what happened? Its capacitance is adjusted to 10 picofarad. So we have changed it from C initial, which is 100 picofarad, to 10 picofarad, sorry. Change it to 10 picofarad. Okay, so calculate the final potential difference across the capacitor. So, isn't it a bit too simple? Final potential difference across the capacitor means voltage across the capacitor. So voltage across the capacitor final is the same as the voltage across the capacitor initial. So it will be 25. Okay, the answer is 25. But we should probably elaborate it a bit. So let's say that since the capacitor remains connected to the battery, okay, it remains connected, the voltage across the capacitor, or the potential difference across the capacitor, they are the same thing. Okay, the voltage across the capacitor will still be 25 volt when fully charged. Okay, when you fully charge a capacitor, it will be equal to the voltage of the power supply. So since we do not change the power supply and we still remain connected to the power supply, so the final voltage will still be the same, 25 volt. Okay, so voltage across the capacitor final will be equals to 25 volt. Okay, question B, the final charge stored in the capacitor. Well, I think that's a bit too straightforward. Okay, we know that the Q final will be equals to the C final multiplied by the V across the capacitor final. Okay, it comes from the equation C is equal to QV. It's unnecessary too many subscript here already. Because there's voltage of power supply and there's voltage across capacitor. That's why I clarify as calling it as VC. Okay, but actually you write as Q is equal to CV. I think all of us understand. But we have to use the Q final, we have to use the C final, we have to use the V final. Okay, C final we know is 10 picofarad, so that's 10 times 10 to the power of negative 12. Okay, then VC final, the voltage across the capacitor final, what we said earlier is 25. So if we calculate it, you get your answer, which is 250 times 10 to the power of negative 12 coulomb. So this one is 250 picocoulomb. Okay, so that will be the final charge stored in the capacitor. Okay, it's a very direct, simple question, but it helps us to understand what remains the same, what has changed. So in this case, if your capacitor remains connected to the battery when you do something to the circuit, the voltage will not change. Okay, if it's remain connected to the battery, the voltage across the capacitor will not change. If you insert a dielectric, if you remove a dielectric, if you do something to the capacitance, the voltage across the capacitance will not change if it is connected to the battery. So this is what we learned through this question over here. Okay, if we remove the battery or we disconnect it from a battery, then it will enter an isolated case. Okay, means by the capacitor is now isolated from this from anything. So if it's isolated, what remain constant will be the charge stored in the capacitor, because there's no pathway for us to move the charge from positive plate to negative plate or other way around. There's no pathway to flow, so the charge will remain the same even if we insert the dielectric, we remove a dielectric, we do whatever to the capacitance, the charge will still remain the same. Okay, so conclusion, remain connected to the power supply, voltage will not change. Isolate the capacitor, the charge will not change. So that's the message we want to convey through this question over here. That's it for this question. Thank you very much.